Okay, welcome back to Chem 111. We're pretty much done with Chapter 7 here in the OpenStax Chemistry 2nd edition textbook. The chapter is focusing on Lewis structures and geometry and things like that, and not exactly sure how well this would work here, but I want to show you this guy here. This is ChemTube, chem₃².com. I'll provide links here, but we've got this molecule here, SF₃, and you can click in here and drag it around and take a look at it. And I just wanted to show you what an octahedron looks like. An octahedron is a solid object, but each one of these fluorine atoms is considered a face, and there's 8 different faces there, so that's why you get the octa part in the octahedron. So that's SF₃. So that's octahedral. CH4 is, CH4, the formula, where is that formula? Right here. CH4 is methane. And you can click this and drag it around, and you can see that it's not planar. And each of the hydrogens point into the corners of what's called a tetrahedron. So the tetrahedron is a solid that's formed from 4 triangles, basically. Okay, so it kind of looks like that. But anyway, this carbon has a geometry that's tetrahedral. Now the electronic geometry of methane as well, ammonia as well, is tetrahedral. So because remember, those 2 electrons that are a lone pair on nitrogen are invisible, but they're occupying this space up here on top of the molecule. And that causes these hydrogens to bend down, and you adopt a trigonal pyramid geometry, but the electronic geometry is tetrahedral as well. Okay, water we've already talked about. This one's really big here on the screen. Water we've already talked about, as being bent. It's not a linear molecule, because if we twist it sideways, there's 2 lone pairs of electrons that are occupying this region. And so here are the 2 lone pairs, and the lone pairs are pointing into the corners of a tetrahedron, and these 2 hydrogens also. So when you have 4 electronic groups, the electronic geometry is tetrahedral. So I don't think I want to mention anything else on this page here, but that's basically what I wanted to show you there. Okay. Now, let's just recall how to make a Lewis structure. You create the skeleton, and you place the less electronegative elements inside. The more electronegative outside. And generally, you attach any hydrogens on the very, very outside. Okay, not to the central atom, but to these atoms here. Okay. Step 2 is, remember that you add your valence electrons, and that's according to the main groups in the periodic table. So you have groups 1 through 8. You're going to have up to 8 dots for xenon, for example. And then what you want to do is add a dot, an additional dot, for a negative charge. For each negative charge, if you have carbonate, for example, you're going to have 2 extra valence electrons for that -2 charge. And these 2 dots are placed on different atoms. Never put 2 dots on the same atom to create a -2 charge, unless of course you're doing something that you have no choice, like oxide. You remove a dot for a cation, and then you make lines. I call that the dot-to-dot procedure, right? You make bonds using those valence electrons. It's okay to violate the octet of the central atom, but all of your main group elements less than element 13, aluminum in the periodic table, need to have an octet, okay? Or a duet in the case of hydrogen, beryllium, those ones, okay? And I was surprised to see that in the textbook there's more than 100 problems, practice problems in the back of the book, and I suggest doing those. I'm not going to waste your time here, doing that, okay? Now, Chapter 8 is called Advanced Theories of Bonding, and let me take a look here at the schedule, Chem 111, and here I'll even show you what I'm looking at here on my screen, my computer screen anyway. It looks like we're doing, starting to get into Chapter 8 today. Chapter 8, November 23rd, and there's no class on Thanksgiving or lab. So anyways, we're going to do those Chapter 8 for a few days. I don't think Chapter 8 would take 3 whole days to do, but we're going to take a look at some concepts in here, okay? I don't look too much into molecular orbital theory and things like that, but I definitely would go through as much as you possibly can in Chapter 7 to work on those problems, okay? There's so many different molecular formulas and drawing them, and Lab 13 is very similar. So if you struggle with Lab 13, take a look at the end of the chapter problems and, kind of go from there, okay? Now, we've already talked about Chapter 8 a little bit, about what bonds are. Bonds are formed between the sharing of 2 electrons, okay, the sharing of 2 electrons. And I would do this on the board if I knew how to work the projector. Everything's broken now that classes are not in session. But we've got this diagram here, okay? So we have energy on this axis here, and then we have something called the internuclear distance. That's the distance between the 2 different nuclei of the hydrogen atoms, okay? So we kind of work from right to left as we describe what's going on here. So when 2 hydrogen atoms are very, very far apart, they have no interaction, so the energy is 0, okay? And as these atoms start to get closer and closer and closer together, they begin to experience an attraction for each other. And it kind of seems counterintuitive because this atom has hydrogen, has electrons, this big, huge electron cloud. Electrons are negative. And this has a big, huge, cloud of one electron anyway. And these electrons from the different atoms should repel each other, right? It just doesn't make sense. Why would they be attracted to each other? And they're neutral, okay? They're not opposite charges. So why would they be attracted to each other? Okay? The reason for that is very complicated. I'm not going to lie to you and make it as simple as what we explain to you in this book. The reason for that is quantum mechanics, okay? But we're just going to dumb it down really bad and just tell you and pretend that the reason why is because electrons on the left hydrogen atom see the nucleus, okay? They see the nucleus of the hydrogen atom on the right, which is positively charged. So these electrons on the left are attracted to the proton or the nucleus on the right. And at the same time, electrons from this electron cloud of the hydrogen atom on the right see the positively charged proton on the left, and so these electrons are attracted to that proton. So the electrons become a little bit confused. Hey, which atom do I belong to? I kind of belong to both. This is great, I can choose, I can pick, and they're kind of coalescing and enjoying that bond. Now, and that's at a ideal hydrogen bond length, and that's going to be a minimum. So that's the energy of that's the energy that you have for the bond distance, okay? And that's the most stable arrangement, okay? So hydrogen monoatomic isn't very stable, but you go downhill, and that's the lowest energy. That's where they want to hang out. Now, as you take these 2 hydrogen atoms and you cram them closer and closer and closer and closer together, the energy starts going up dramatically through the roof, okay? And the reason why is because now the internuclear repulsion begins to dominate. Okay, what does that mean? Well, it means the nucleus on the left, since it's positively charged, is now going to be very close to this nucleus on the right, which is also positively charged, and like charges repel. So that's a repulsion of the nuclei, and the energy is very, 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 very high, okay? In fusion experiments, whether we're talking about in the sun or here on Earth, maybe in a thermonuclear hydrogen bomb, or maybe some kind of tomahawk reactor in Japan, say, for example, you're trying to get these two hydrogen atoms to fuse together to form a helium nucleus, and that's going to release quite a bit of energy. But you have to overcome this Coulombic repulsion, which is like off the page and probably like 5 feet in that direction. Okay, so that basically is what we call the valence bond theory. Okay, it's the theory of how a bond forms. And you've got all of these different bond lengths, you know, and energies and things like that. Okay, so that's a little bit there about the book. Now I'm skipping these kind of things here about orbitals. Like I said, it's very complicated, and it gets into a lot of quantum mechanics and things like that. And they're just showing these little pictures and, oh yeah, this is cool and stuff. But to really understand this, you have to really get in great amounts of detail. But what I want to discuss are sigma bonds and pi bonds, okay? Sigma bonds and pi bonds. And it's a very simple thing to discuss. And they happen in things that you have a multiple bonding, okay? So we'll talk about this right here, right now. All right, so back to the blackboard here. All right, so what is a sigma bond? Sigma is a name for a certain type of symmetry, and it means symmetry along the axis. It's a Greek letter. It looks like an O with a kind of a curlicue coming off the top of it. Makes me think of a baby with only one little piece of hair they're combing, or maybe Homer Simpson or something like that. So this is the Greek letter sigma. A sigma bond is any single bond. Okay, that's all you need to really remember. So if we take a look at this molecule here, this is called ethane. This guy right here has 1, 2, 3, 4, 5, 6. It contains 7 sigma bonds. Okay? Now, a pi bond is a multiple bond. It can be a double bond or a triple bond. Okay? And pi, you know, that's your Greek letter for P. We're familiar from math, pi. Okay, so it's not too difficult to remember that one. And this is a multiple bond, okay? A multiple bond. Okay, and there's a whole bunch of stuff that goes in here with hybridization and bonding and things like that, but let's look at this molecule here. All right. Oh my, oh me. Okay, I messed that up. Let me erase one of those. Okay, there we go. So this molecule, let's count the green bonds. 1, 2, 3, 4, 5. This has 5 sigma bonds. Okay? And it contains 1 pi bond. Okay? 1 pi bond. So the way you count these things is the multiple bond is 1 sigma bond, and each additional multiple bond is a pi bond. All right? So be careful when you count. Let's look at ethylene. Or not ethylene, acetylene I meant to say. And I'll draw the multiple bonds in purple. Okay? So we call this a triple bond, right? But when you count 1, 2, 3. So everything has a single bond. There's 3 sigma bonds. And then in purple, we have 2 pi bonds. Okay? Yeah, pi bonds are very weird. They're formed with p orbitals, and sigma bonds are formed generally with hybridized orbitals. Okay, so that's how you count. Let's look at some. Let's count. Let's do some examples. So we want to count how many sigma and pi in things like H₂SO₄. okay? So remember how to do this. You create your skeleton, you add your dots, you make your lines, all that kind of stuff. So and we make our bonds here. Now, I would go crazy if I switched from purple to back to green, so I'm just going to draw everything with a green colored pen here. All right, so I'm trying to be careful with my lines. All right, and now we count. So what I suggest doing is take a different colored pencil or something like that and just draw on top of what you have. So here's a double bond. So only the second part of this multiple bond is a pi bond, and only the second part of this multiple bond is a pi bond, okay? So let's count the greens. 1, 2, 3, 4, 5, 6. That's 6 sigma and 2 pi. All right, you do need to be able to draw a Lewis structure. I mean, that's, of course, the point of this. How about SO₂? Let's do another one, SO₂. All right, so sulfur has 6 valence electrons. If I can count to 6. Oxygen is also in group 6, has 6 valence electrons. Okay, there's 6 and 6 and 6. All right, so, and now we draw bonds. Okay, these oxygens don't have an octet. They always have an octet. There, that has an octet. There, that has an octet. The sulfur in the middle violates the octet rule. Okay, who cares? It's a rule breaker sometimes. Now, highlight that double bond. All right. Highlight that double bond. Half of it anyway. And so let's count. So we got 2 pi's. And we've got 1, 2, 2 sigmas. All right, so that's how you count sigma bonds and pi bonds. I don't need you to do all the quantum mechanics and math to figure out the overlap between the types of orbitals and things like that, okay? Now, what I do want to talk about are hybrid orbitals, and this is very important. Now, the basic idea is as follows, okay? Let's look at water, okay? Now, early on, people had figured out, okay, we know that hydrogen is 1s1, okay? An s orbital is, you know, just a sphere. And oxygen is something like this, okay? So it has s orbitals and p orbitals. So an s orbital is a circle, and a p orbital is this dumbbell thing that's arranged, you know, along the x-axis or the y-axis or something like this, okay? And they thought, well, how does this molecule form? I know we have this dot on the hydrogen, and we have a dot on the oxygen, and that makes the bond. But people were thinking about, okay, well, what exact orbitals are involved in this? If we draw a hydrogen, and then we draw a p orbital, okay, p orbital just like this, all right, there could be one dot in this, you know, 1s orbital, and there could be one dot in this p orbital if we, you know, think about maybe just fudging a little bit where those electrons are. And then they said, well, wait a minute, if this is the px, the other orbital would have to be like a py. So here's another p orbital on the oxygen atom. And this would have to be arranged, you know, 90 degrees with respect to the other one, because the px and the py, right, are 90 degrees. And, well, that's wrong, because we know that water does not have a 90-degree geometry. Water actually has a geometry closer to 104 degrees, right? So these p orbitals are somehow not 90 degrees. They're somehow 104.5 degrees. So this was the problem, okay? And they came up with a whole bunch of different ideas. And gosh, it would take me forever to read the book to you. But basically, they had this idea that hybrid orbitals are mixing of orbitals to create different orientations. Okay, that's the main thing. And then the set of atomic orbitals mixed to form all this other stuff. Okay, so let me show you what happens, okay? It's mixing. And these are called hybrid orbitals because you're mixing these orbitals. So here is an s orbital, and here's a p orbital. Don't worry about the pink and blue. These are the different phases of the wave function, okay? So you got this, you mix them together, and then you separate them out, and you form two different sp hybrid orbitals, okay? So they're a mixture of the two. They're kind of fatter because the s orbital is more of a sphere and it has orientation, okay? Because the blue and the blue reinforce, or the blue and the red don't reinforce. So anyway, it looks weird. It looks like a p orbital that's like super big on one side and then there's just little knob on the back side, okay? So it looks weird, all right? And perfectly, the math comes out such that the angles are exactly 180 degrees apart from each other, okay? And they have an orbital diagram shown here. So we have, let me angle it this way. So we got 2 electrons in the s orbital, let's say. Why there? Well, because this is lower in energy. And then we have 0 electrons in the p orbital, okay? And then when you hybridize it, you get sp hybrid orbitals, okay? Different energies for those, all right? Now, with this 180 degrees, what can you do? You can form different types of bonds. So for example, let's look at BeF2. Beryllium, okay, we have talked about is like the helium core, right? With so beryllium is element number 4 in the periodic table. So it's got the helium core, and then it's got 2s2, okay? And then fluorine, remember, is also the helium core, but then you've got all these valence electrons, 7 of them, okay, 2p5. So you got 7 valence electrons and 2 there. So what happens is the s orbital from the beryllium and the p orbitals, which are higher in energy, okay? So we kind of just ignore those s orbitals there, which I think is kind of wrong to do, but that's what people do. So these s and p mix, okay, to give sp hybrid orbitals. And the math just works out so great that they're orientated so here's one of these sp hybrid orbitals. Sometimes we leave that little back lobe off because it just looks confusing. And then fluorine, it's difficult to say what item is in there, but let me redo this. Where am I? Okay. All right, so let's talk about the bonding in BeF2. Actually, BeH2. All right, so beryllium, if you remember from the periodic table, is element number 4. So it's got a core and 2s2. Okay, so we got s electrons, and we technically have 0 electrons in the p shell, right? There's 0 electrons in the p shell. There's just, it's in group 2. It has 2 valence electrons. It's got s orbitals that are filled, and it's got empty p orbitals, okay? not a really interesting bookshelf. Now, hydrogen, as we all know, is just has one s1. It's got an s orbital, okay? So what we do is we need to create those bonds of 180 degrees. So we take the s and the p, and we make two new orbitals. So here's an s orbital, here's a p orbital, and you make one orbital going to the left, let's say, and another orbital going to the right, okay? And so if we write the this kind of a balloon drawing here showing what the orbitals are involved, we can show one of these sp hybrid orbitals going to the right. We can draw hydrogen here with one valence electron or a dot there, right? And then beryllium also has a sp hybrid orbital going to the left. That's just a hydrogen atomic orbital. And there's one dot there, right? And then hydrogen is right here, okay, with one dot. And mathematically, it just works out so great that these are aligned 180 degrees with respect to each other. Okay, so what do you need to remember or know or learn to recognize? You draw the Lewis structure of BeH2, okay, and you get something like this, okay, and it has two electron groups. So therefore, it's sp hybridized. Okay. The way I tell my students to memorize this or remember this is that if you have one s and one p, 1 plus 1 is equal to 2, and that's how you know you're talking about that. Okay. Let's now talk about the bonding in BF3. Okay. Now, BF3 is experimentally known to be trigonal planar. Okay, so we need angles to be 120 degrees. How in the heck do we do that? Okay. So let me show you in the book what's going on here. Alrighty. So this topic is sp² hybridization. Okay. And what we're going to do is take the s orbital, the p orbital, and a different p orbital, take all of those things and mathematically combine them and generate 3 new p orbitals. Now it's hard to see in this diagram here, but they're all orientated 120 degrees away from each other in that xy plane. Okay? So yeah, it's pretty cool. So mathematically, it just magically works out that it's exactly 120 degrees with respect to each other, okay? And there's a whole bunch of math. We just show it pictorially here, how it's going on, okay? And that's hybridization. Now, I watched a YouTube video by somebody teaching high school, I think it was, and they had, they said, what is hybridization? And they had a p orbital. Actually, they had Play-Doh, believe it or not, in the shape of a p orbital with blue, and they had a another piece of Play-Doh that was yellow, and they took those 2 pieces of Play-Doh and they just totally mashed them together. And what they did was they put on the tabletop 2 new orbitals that looked like this, and they said that's hybridization. Okay, you mix these 2 things and you get 2 new weird-looking orbitals that have slightly different shapes and different orientations. So let's take a look at BF3. Boron, if you look at the periodic table, is element number 5. Okay, so you've got your helium core, and you've got an electron configuration of 1s2, 2p1. All right. It has 3 valence electrons. So that's why when we do the Lewis structures, we start off with 3 dots. All right. Now, in order to get these things all aligned 120 degrees, instead of just whatever with the p orbitals being 90, they take the s, the px, and the py, so a couple, 3 pieces of Play-Doh. Okay, you're starting with 3, and you end up with 3. You end up with sp2, sp², sp². And they don't really have labels for these that I know of. So yeah, they're all equivalent, degenerate, and they're pointing in different directions. They're all going to be pointing into the corners of a triangle. Okay, so our three dots, very trivially, were drawn like that. Now we can think more geometrically how those dots are being aligned, okay? So they're like that, all right? So that's how the 3 valence electrons are actually positioned in your sp² hybrid lobes, okay? These are hybrid orbitals created by mixing atomic orbitals. And then you've got your fluorine. You know, it might be difficult to explain this, but you might choose to use a p orbital on fluorine. Okay? So what does a p orbital look like? It looks like a dumbbell shape. And why am I drawing only one dot? Because each bond is formed from, you know, one electron from each element, right? Okay. And then you got like a whole bunch of lone pairs. I won't draw them all in there because it kind of gets confusing with this drawing, okay? So what do you need to know? What do you need to recognize? How do you do this? You need to be able to take something like BF3, draw the Lewis structure for BF3, okay? Count the total electron groups. There are 3 total electron groups here. So therefore, we would label it as sp² hybridized. Okay? This boron atom is sp² hybridized. Now, how do you remember this? How do you memorize this? sp² is like saying S1P2, and 1 plus 2 is 3. And so that's how you remember that, oh, it's 3 electron groups, it must be sp². Okay? So anything with 3 total electron groups is going to be sp². Another example would be carbonate. Carbonate, as we saw previously, has this crazy looking Lewis structure with a couple different formal charges. And when you count the electron groups, 3 groups, is predicted to be sp² hybridized. Okay, so we're always looking at the hybridization of the central atom. All right, so we've done sp², we've done sp3, we've done sp, we've done sp², and what do you think is next? That's right, it's sp3. So if we take a look at the textbook, this is a much more complicated example because you're taking the s orbital and you're taking all of the 3 p orbitals, right? You've got the px, the py, and the pz, and you're doing this magical hybridization step, which is really just a bunch of math. And you're getting 4 different sp3 hybrid orbitals. So if you start with 4, you end up with 4. And this gives a tetrahedral arrangement where each of these lobes or these electron clouds or hybrid orbitals are pointing to the corners of a tetrahedron, okay? Which is pretty good. And so it has an exact orientation of 109.5 degrees with respect to each other. The same exact thing we would say from VSEPR theory. So it's pretty complementary, okay? So let's take a look at methane. Okay, hydrogen we know is just 1s1. We're going to represent it today as a circle with a dot. Okay, that's our s orbital with 1 electron somewhere in there. And carbon, if you look at your periodic table, has a core of helium. Okay, and it's got 2s2, 2p2. Okay, and so once again, we have 4 valence electrons. And that's why we start off the Lewis structure by drawing 4 dots on the carbon. But now we want to think more carefully, completely about where those things are. So you take this s orbital, okay, and you take all three of the p orbitals, so 1, 2, 3, 4 total, and you mix all of these up, okay? Plus, minus, and I don't remember the percents and all that, and it's very three-dimensional math. But you get an sp3, an sp3, an sp3, and an sp3 orbital, okay? And these all point to the corners of a tetrahedron. So the lame way of doing this would be to do a Lewis structure, right? Or we just draw dots and make it very two-dimensional looking. But we can draw this now as best we can. So there's my carbon. The dot there is in that hybrid orbital, and this dot is the hydrogen, right? The hydrogen. And so here's another hybrid orbital coming off to the bottom left of the screen here, and we'll put one valence electron there, and so we'll do hydrogen. We'll put a dot there, so that's a bond. And then, gosh, how do you draw these going in and out of the screen? Because this has to be a tetrahedral three-dimensional shape. I think I will draw this one bold. So that means it's coming towards us. I just invented a new terminology here. And so that one's coming out towards us, right? So that's why I'm making it bold. So you got that one electron there. So that makes a bond. And how about the one that's going away? I don't know. I'll just draw it as a dash. Why not? And so my hydrogen atom, which has one electron in the s orbital, is now interacting with that. Okay, so these are sigma bonds. These sigma bonds are made from an sp3 hybrid orbital, right? Which is, remember, an orbital is just an electron cloud, and this happens to be an atomic orbital. This hydrogen is an s atomic orbital. Okay. So you know, two dots make a line. That's a sigma bond. All right, so we're kind of embellishing the Lewis dot structures to look a little bit more complicated to match the geometry of the VSEPR theory. Okay. I think I had a student call these balloon drawings once, or party balloon drawings. This right here is carbon. That dot in the very middle is carbon, and you can see these four lobes. Those are four different sp3 hybrid orbitals, and here's a hydrogen, 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 and then we have the same thing over here, and another four lobes. And these all come together, and you'll see that you form this molecule here. Now what is that? That is C₂H6. Okay? How would we normally draw C₂H6? We would draw it like this, okay? Carbon has 4 bonds to it. Whoops. Carbon has 4 bonds to it. Okay. And hydrogen always has 1 bond. So all of these angles, I don't care which one you pick, are going to be 109. Okay. So that's your tetrahedral geometry shape type thing. Okay. Now I'm not going to go into this in great detail here, and I'm very thankful the book doesn't really talk about this. I thought I saw it online though. I don't know, maybe the new edition textbook does. I'm scared to look. But we've got these sp³d and sp³d² hybridizations, and they're crazy things that look like this. And we have some diagrams that show kind of like what they look like. Very interesting. And over here on the next page is an octahedral, and we've got all these sp³d²s. Okay, so let's take a look now what we need to be able to do with methane before I talk about those. If you have a structure of methane, you need to draw the Lewis structure that looks like this. Count the total electron groups. And then figure out what that is that sp, sp2, sp3, what? Okay, it turns out to be sp3. Now, the way you figure this out or remember this is that we have one s orbital and a maximum of 3 p orbitals, right? And if you add those two together, you get the same number as your electron groups, okay? So that's how you keep track of sp, sp2, and sp3. You count the groups and then you figure out what is the hybridization. Now, when you have something that has more groups attached to it, you do the same thing. So here's this ClF₃. It's this weird T-shaped geometry, and it's one of like 2 molecules that have this, I think. Anyways, when you count the groups, you do 1 group, okay, 2 groups, 3 groups, 4 groups, 5 groups. Remember, a group is a bond. It could be single, double, triple, or a lone pair, like a double, 2 electrons. And so this would be sp₃d. Now, how do you remember this? Okay. The way you remember this is that in the periodic table, there's only one s orbital, right? The s block. There are 3 p orbitals maximum. 1 plus 3 is 4. We need 1 more to get 5, right? So 1 plus 3 plus 1 is 5, and that matches the total number of electron groups of this crazy-looking molecule. Okay, so that's sp₃d hybridized. Okay, that is sp₃d hybridized. Okay. How about an octahedral one? We've got SF6, which I believe was drawn there in the book. SF6 looks like this. If I slap it together quick. Okay, we count electron groups again. So there's 1, 2, 3, 4, 5, 6 bonds. 6 bonds means 6 electron groups. And that's going to mean sp₃d2. And thankfully, we stop there. Do not worry about d orbitals. Okay? Do not go online and find out about that. So let's see. How do you remember this? You just count the groups and you see what matches, right? So you have 1 s orbital maximum. You have 3 p orbitals maximum. You have a whole lot of d orbitals, but you don't need to go that high. To get 6, we just need a 2 here, okay? So 1 plus 3 plus 2 is equal to 6, and that matches the electron groups, okay? Let me see if there's a summary table in the book. Yes, here we go. I don't need to write it all out. So what you do is you count your electron groups, your total electron groups. If you have 2 groups, it's going to be a linear geometry from Vesper. It's going to be sp hybridized, and here's a little pictorial of that, okay? If you have 3 groups, it's going to be triangular, okay? We call it trigonal planar in Vesper language. We would say it's sp2 hybridized, and that's what the orbital lobes look like of all the different hybrid orbitals. If you have 4 groups, it's going to be tetrahedral. We call that sp3 hybridized, and the angles are 109.5, the same exact as Vesper, okay? So tetrahedral and Vesper would tell you about the same angles. If you have 5 total electron groups, Vesper, we would call it trigonal bipyramid, and here would be your angles, 90, 120, and also 180. But now we're learning this hybridization now. We would call it sp₃d hybridized, okay? When you have 6 total electron groups, it's going to have an octahedral geometry as before, and your angles are going to be 90 and 180 degrees as before. And the new thing here today is the hybridization. It's sp₃d2, okay? So it goes sp, then sp2, then sp3, and then you stop. You never get sp4, right? this p does not mean, this 3 does not mean 3 electrons, it means 3 p orbitals. Okay, this 3 means 3 p orbitals. That's a little bit of a different notation. And then sp₃d² is the highest we go, okay? So this notation is not electron configuration, it's hybridization. So you need to remember 2, 3, 4, 5, 6, and this column, okay? And, you know, that's basically it. So you might have some kind of questions like that. You know, what's the hybridization of the central atom in sulfate? So you first construct the core here, right? And the surrounding oxygens are more electronegative. That looks good. Now you look in the periodic table, both sulfur and oxygen are in group 6. So they're going to have 6 valence electrons. Okay, so that's 6. And, oh yeah, don't forget the sulfur. Sulfur has 6 as well. And then what you'll want to do is modify for the charge. So I'll use blue here. So -2 means you add 2 more valence electrons on different atoms, usually on outside atoms. So I'll add 1 here. That makes this oxygen negative. I'll add 1 electron here. That makes this one negative. And then I proceed to making bonds. Okay, so make a bond here, make a bond here. Let's see. This oxygen does not have an octet yet, so share more. Okay, that's good. How about that? Hey, yeah, that oxygen has an octet, 2, 4, 6, 8. So we stop there. We just need a single bond for that. And same thing there. Okay. Now that we have this crazy looking thing, which is called sulfate, by the way, it's called a sulfate ion, we count total electron groups. Now remember, an electron group can be a double bond, it can be a single bond, okay? So these are basically my lobes, my orbital lobes, right? 4 groups, and we want to figure out what it is, okay? So there's a maximum of 1 s orbital. I need this to add up to 4, so I do that, and I don't need any d's, right? Because 1 plus 3 is going to be equal to 4. Okay, so the answer is sp₃ hybridized. Okay. The other one is this crazy looking molecule. This is called urea. Humans produce about 10 grams of it a day. It's used as a fertilizer, and the source does not come from humans, by the way. But we want to know what is the hybridization of each nitrogen and carbon in urea. Here's nitrogen, here's carbon, here's urea. And it's got a funny Lewis structure. So what we need to do is kind of look at this condensed molecular formula to figure out where things are. And these 2 hydrogens are bonded to this nitrogen. This oxygen is bonded to this carbon. These 2 hydrogens are bonded to this nitrogen. So it's going to look like this is a central atom here. So we've got a carbon in the middle, got oxygen, nitrogen, nitrogen, and then we got all the hydrogens connected to the H's. Okay, H here, H here, H here, H here. Now for your Lewis structures, you want to place 4 dots on your carbon, 5 dots on the nitrogen, the hydrogens all have 1 dot. The oxygen has 6 valence electrons. So we go ahead and now make our bonds. So everything must have a single bond at first. And we stop to evaluate the octet. Now this oxygen does not have an octet, and this carbon does not have an octet. So I'm going to need to make another bond between the oxygen and the carbon. And now I'm done. That's a good Lewis structure. Okay? And then just like we did with aspirin and other very large molecules, you want to isolate each atom and then count how many groups you have to that atom. So if we look at nitrogen here, this nitrogen has 1, 2. The whole molecule is a third group, but I'm just going to circle the bond. And then 4. Okay? So 4 groups is going to be like methane, which is sp³ hybridized. This nitrogen over here, let's see, 1, 2, 3, 4. Okay, so that nitrogen also has 4 groups, which is also sp³ hybridized. Now how about the middle oxygen? Let me see, I'll switch to a white colored thing here. So this carbon is bonded to this electron group, this electron group, this electron group. So carbon has 3 groups, and remember we call that sp². sp². All right, so if you could do something like that, you got it made. Okay, you got it made. All right, I'm going to stop here today. We're pretty much done with the chapter. I just need to talk about maybe multiple bonding, and that's about it. Okay, and the rest of the chapter is very highly specialized for some things that I just skip. Okay, probably get into chapter 9 gases maybe a day early. But anyways, that's it for today. Check out the homework. Let me know if you have any questions. Have a good day.